Partial derivatives. So these are derivatives of a function of two or more variables. Example. Suppose the total cost of manufacturing a product with material costs x and labor costs y is given by this function of two variables. C of xy equals 5x squared plus 3y squared plus 10. So we're interested in the rate of change of the cost here of this function with respect to material costs and labor costs. So as one of those things changes, how does the total cost change? Right, so if we spend one more dollar on material costs, the total cost will go up by some amount. And if we spend one more dollar on labor costs, the total cost will go up by some other amount. That amount is the rate of change of cost. It's a derivative. So here's the definition, and we spent a lot of time with just like the notation and the lingo here. So if z is a function of two variables, x and y, so z is some 3D surface, we find the partial derivative of z with respect to x, denoted, so that's not a d, that's a delta, that's a squiggly d. We denote it dz dx, so that should be familiar, the change in z with respect to x. Remember, delta literally means change in math. So we use the squiggly d delta to distinguish this from a derivative of a function of one variable. If you see the squiggly d, we're talking about a function that we can take derivatives with respect to several variables of. Okay, so how do we do it? We treat y as a constant. And that's really the trick here. This isn't hard. You just treat the other variable as if it's being held constant and use all the rules that you normally use to find a derivative. Same thing if you're doing dz dy. And I have, before you get too nuts drawing those squiggly d's, I have notation that I like better that I'm going to use from here on out, but you're just going to see that in the book and in the future. So same deal. To find dz dy, we just treat x as if it were a constant. So if it helps you when you're doing this, just think of x as a constant. Think like a specific one. Think of it as 5. Like what would happen? What would you do with the derivative? You'll see. Here's some other notation you might see. You might just see it written d dx because you obviously know what function you're referring to. You might see f for z with a little subscript x. That means the same thing. You're taking the derivative with respect to x. Or you might just see f with a subscript x or z with a subscript x. That's what I like. I'm going to use that final notation. So instead of dz, squiggly dz, dx, I'm just going to write z with a little x in subscript. And that's going to tell you that you're taking the derivative of z with respect to x, not some other variable. Example, in the manufacturing cost example, we had 5x squared plus 3y squared plus 10. So here it goes. The partial derivative of the cost with respect to x is, okay, that first term is 5x squared. So the derivative of that thing is just 10x, right? 2 times 5x. The next term is 3y squared. But y is a constant. So that might as well be the same as 3 times, 2 squared or something. It doesn't matter. The derivative of a constant is 0. So that goes away. Just like the next term, which is 10, the derivative of a constant is 0. So nothing survives that. So you see what I'm saying? Only x gets treated as a variable. All the other stuff gets treated as a constant, which is nice because when you're differentiating, constants just generally go away. So cx is literally just 10x. Do cy, it's the same exact thing. 5x squared, as far as y is concerned, is just a constant. So it just goes to 0 on the derivative. The derivative of 3y squared is just 6y, right? Power rule. And then the derivative of 10 is nothing. So the derivative of that cost function with respect to y is just 6y. And that's it. See, that's not that hard. You just have to, it's just something to get used to, just treating the other variable like a constant. So let's interpret. What the heck does that mean? So let's see, X was material cost. So that's the rate of change of the total cost with respect to material costs. So if we raise our material costs by $1 and our labor costs stay the same, then our total cost will go up by $10. 10 times 1. That's it. Same thing with labor costs. If our labor costs go up by $1 and our material costs stay the same, then our total costs will go up $6. So that's how you interpret a partial derivative. We like to visualize these things, but again, this is all 3D graphs. So I do want to give you an example now of how, like, what are we doing? Like, visualize what we're doing in terms of like tangent lines and stuff. So look at the graph. To visualize the derivative of z with respect to x. So z is that blue curvy surface. If we were going to graph z, that's what it would look like. So what we do is we hold y constant. What happens if we hold y constant? So if you look at like the equation y equals 2 or something, what is that? It's a plane, right? It's a set of all the points. It's that purplish plane. It's a set of all the points where y equals 2. So that plane intersects with that surface. And if you picture the intersection of that plane and that surface, what does that intersection look like? It looks like a two-dimensional curve. It looks like a normal curve from normal calculus. So now you can picture a tangent line at some point along that curve, at any point, right? So what dz dx is the slope of that tangent line at like some specific point x. So we are still measuring a rate of change, but we're just imagining, okay, y stays constant, and now we can move x around back and forth. That's what dz dx is. It's the rate of change of the curvy thing with respect to the variable x. Same with dz dy. If we hold x constant, that looks like a plane that's parallel to the y-axis, right? So you look at where the plane intersects that blue surface, it intersects it in just a 2D curve. So it looks like as we go that way, right, the slope of the tangent line looks to be increasing. So dz dy would be positive because the function is increasing and going up, and the function is increasing with respect to going that way. Let's just practice this, right? Let's just jump in and do a hard one because they're not that hard. They're not as hard as integrals. So here's a made-up function for z of xy equals natural log of 1 plus x squared y minus y e to the negative x. We're just going to find both the partial derivatives. Maybe a good spot to pause the video and just do it yourself if you're confident. So to do zx, we are treating everything else like a constant. So we have the natural log of some function of x, right? 1 plus x squared y is a function of x. So the first part of it is going to be 1 over, right, derivative of natural log, 1 over 1 plus x squared y times the derivative of that. Now, 1 just goes away. Y is being treated as a constant, but if it's a constant multiplier, the derivative of x squared y is going to be 2xy. Agree with that? So it's going to be times that by the chain rule. And then in the next term, okay, it's y times e to the negative x. Y comes along for the ride, like constants do. And then the derivative of e to the negative x is e to the negative x times a negative 1, because the chain rule makes that little negative 1 hop out. Okay, so there's all that stuff I just said. 1 over 1 plus x squared y times the derivative of 1 plus x squared y, which is 2xy, minus y times e to the negative x times the derivative of negative x, which is negative 1. And then you can clean that up. I guess you don't have to, but I'm going to. 2xy over 1 plus x squared y plus, just all that happens there is the negative signs cancel out, plus y e to the negative x. Okay, so that's the partial. It's called a partial of z with respect to x. Let's do y. Same deal. So it's 1 over 1 plus x squared y. Okay, the derivative of 1 plus x squared y, 1 is still a constant. X squared is also a constant. So x squared might as well be 16 or whatever. The derivative of x squared y is just x squared, because the derivative of a constant times y is just the constant. And then minus, okay, y is the variable, e to the negative x is also just a constant, right? If x is a constant, e to the negative x is also a constant. It's just e to some power. So the derivative of y e to the negative x is just e to the negative x. And that cleans up to that. So it's different, you see what I'm saying? But it's not that hard. You just have to get used to treating it, the other variable, as if it were a constant and just imagining that it is. So we do need these things. If we want to evaluate it at a specific point, that's the notation I use. I like that because it's simple. So zx of AB or zy of AB is just like saying f prime of A. It just means, okay, that's the derivative generally, but what's the derivative at like a specific point? So remember, if x is A and y is B, and z is going to be some other thing based on whatever we define z as. So remember what these numbers actually are. They are slopes of tangent lines, either going that way or that way. So when x is 1 and y is 2, so we still go x, y. And when we're talking about an ordered triple in space, we go x, y, z. So zx of 1, 2, all I mean there is just plug 1 in for x and 2 in for y. You're going to get some specific number. That number is a rate of change, is a slope of a tangent line. So here we go. So it's 2 times 1 times 2 over 1 plus 1 squared times 2 plus 2 times e to the negative 1. That's a number. That's some constant. So you can clean that up a little bit. Looks like 4/3 plus 2 over e. So don't let the e confuse you. E is a constant as well. So that's just some number that gives the slope of a tangent line at a specific point. Zy, same deal. It's going to be what? 1 squared over 1 plus 1 squared times 2 minus e to the negative 1. And then clean that up. That's just some number, some decimal as well. There it is. 1/3, yes, minus 1 over e. So that number is smaller than the other number. And all that means is that at that specific point in space, x is, if you were running along the x-axis, it'd be increasing faster than if you were running along the y-axis, like parallel to the y-axis. So the actual point, like vertically, is just given by z of 1, 2. So when you plug 1, 2 back into the original function, you get that thing, which is what? Natural log of 3 minus 2 over e. That's the actual z value. So if I don't know what the surface looks like, it probably looks weird. But the actual point in space we're focusing on is that. So this is called an ordered triple rather than an ordered pair. Right, so that's what we're talking about when we talk about this stuff. There's a point, that is a point on the wavy surface, and what we just found was zx and zy are the slopes of tangent lines going either parallel to the x-axis or parallel to the y-axis. Nothing's stopping us at 2 variables. You could certainly think of a function of 3 variables, right? Okay, we have material costs, labor costs, I don't know, rent, right? You could certainly add a 4th variable to that if you're just talking about costs. You could add a 5th variable. You can literally have a system in mathematics that has an infinite number of variables in it. If you don't believe me, think of something like the stock market. That's a system that is so complex and so volatile that we literally treat it like it has infinite variables and then just do calculus with it anyways. That's a whole field. It's called stochastic calculus, and you introduce an element of randomness. We don't have to deal with it. But if we were doing math with a function of 3 or 4 variables, it works exactly the same. The partial derivatives work exactly the same way. They're just a rate of change of the function with respect to one of the variables. The tough part is if anything has more than 3 dimensions going on, you can't graph it because our human brains can't conceive of a 4-dimensional or 5-dimensional space. So I can't show you a picture of it, but the calculus does work exactly the same way. So there you go. There's a function of 3 variables. F of x, y, z equals 2x squared y plus zy squared plus x over z. So can't graph it, but why not? Why couldn't you have a function that relies on 3 different independent variables? You could. So doing the partial derivatives is no harder. If you're doing fx, you treat y and z like a constant. So the derivative of 2x squared y is just going to be 4xy. The derivative of zy squared is nothing because those are both constants, so 0. And the derivative of x over z, okay, that's the same as 1 over z times x. So the derivative of that is just 1 over z. Imagine if that's like x over 2. The derivative of that is just 1/2. So boom, there you go. That's it. 4xy plus 1 over z. So see, not harder. Fy, okay, let's see. 2x squared is a constant, so the derivative of a constant times y is just a constant, so that's just going to be 2x squared. The derivative of zy squared is going to be 2zy, because the z comes along for the ride, and the derivative of x over z is 0. Right? 2x squared plus 2zy. Let's do fz. So the derivative of 2x squared y now is 0. The derivative of zy squared is just y squared, because y squared is just a constant. And let me think. The derivative of x over z is going to be, so the derivative of z to the negative 1 is negative z to the negative 2, right? So it's going to be negative x times z to the negative 2, like that. Y squared minus xz to the negative 2. So they're all different, right? That's not always going to be the case. But to do it is, I don't think, really that difficult. And obviously, if a function of 4 variables, you just got more derivatives, but it's exactly the same. 5 variables, whatever. We're not going to like do that just to do it, but you could have it. All we mean by higher order partial derivatives is just like f double prime or f triple prime or whatever. It's just like a second or third derivative. So the difference here is we have more options. So like you can do fx, and then you can take the derivative of that with respect to x again. Or you can take fx and you can take the derivative of that with respect to y, right? Now, if you have 3 variables or you're doing higher than second order derivatives, we have a lot more options. It's like a branching tree. So there are more higher order partial derivatives for these types of functions than there obviously would be for a function of only 1 variable. So the first derivatives are sometimes called the first partials. Musicians, that's also a musical term, and it refers to an interval, like when you're tuning an instrument. Okay, so the notation I like is where you just write zxx. So the derivatives of the first partial derivatives are just called the second partial derivatives, or just the second partials. Just like normal. The derivative of a derivative is a second derivative. Right, so it has 4 of them, because you can go x then x then y then x, or y then y, right? So we have more options for these. You'll see different notation in the book and whatnot. Deal with it. I like this the best because it's simplest. Zxx means do x then do x, and obviously I'll do an example. Zyy means do y then do y. Zxy means first you do respect to x, then respect to y. Obviously, that means the opposite. First do y, then do x. So just read it from left to right, and just do them in order. With a function of 3 variables, if I ask you, like in the previous example, for f x, z, y, you do x, then z, then y. Okay? Simple example, okay, we have z, which is a function of 2 variables, x and y. It's xy squared plus 4xy minus 5. We're going to find all 4 second partial derivatives of z. So the first thing you do here is find the 2 first partial derivatives, zx and zy. Easy. Zx is okay. Y squared x, y squared is a constant, so that's just y squared. The derivative of 4xy, 4y is also a constant, so that's just 4y, and the 5 goes away. Let's do zy. Zy, okay, the power rule, so it's 2xy, and the derivative of 4xy is just 4x, because that's just a constant, and the 5 goes away as well. Okay, so there's our 2 first partials, and now we just have to do derivatives of both of those with respect to x and y. All right, so zxx, well, look at zx. Zx is y squared plus 4y. What's the derivative of that with respect to x? It's nothing, right? 0. Those are all constants. Zxy, okay, now we got to do the derivative of that with respect to y. So the derivative of y squared is 2y. The derivative of 4y is just 4. So it's just 2y plus 4. Zyy, okay, the derivative of 2xy is just 2x. What's the derivative of 4x? It's just 0. So the only thing here is that 2x. Zyx, okay, the derivative of 2xy is just 2y, and the derivative of 4x is just 4 with respect to x. So it's just 2y plus 4. There they are. We could go farther. We could do z, x, y, y, obviously. We're not going to like push it for no reason. And these things do have a concrete interpretable result, just like they do with one variable. You're right now noticing that zxy and zyx are the same. That is in fact always the case if the derivatives are continuous. So think about a spot where the derivative is not continuous, like a spike, right? That wouldn't be. But there's a theorem out there that just says if the function and its derivatives are continuous at some point, so just imagine a smooth point along a 3D surface where everything's going fine, like a wave, that's always going to happen. And in fact, you can use that to test it. If you want to prove that like a function is continuous and differentiable at a certain point, you can do that. So this is like it goes both ways. So there's that. Again, that'll always happen if the function is continuous and has continuous first and second derivatives. It's just an interesting thing that happens. So that for your purposes, that's just like if you get that, you know you're right. One example, just to round it out, let's go back to this Douglas-Cobb production model. A company's production Q can be modeled by Q of KL, so that's a function of two variables. Maybe one of these days I'll show you the graph of a Cobb-Douglas function. Is 140 times k to the 1/2 times L to the 1/2. So remember, those two exponents always add to 1 in this sort of production model. So K is the expenditures in thousands of dollars, and L is going to be labor hours. That's generally how Cobb-Douglas functions work. So we're just going to take some derivatives of this thing and interpret them. We're going to find both partial derivatives, and specifically when, expenditures are 250,000 and labor hours are 1225. And then we're just going to say, well, what is that? What did we just do? Okay, QK, okay, so K is the variable, so by the power rule, the 1/2 comes out front, the constant 140 comes along for the ride, and then the power of 1/2 drops down to negative 1/2. The L to the 1/2 in this case is also a constant, so that also just comes along for the ride. We can clean that up a bit. 1/2 times 140 is 70, obviously, and then it's like it's over the square root of K, and then there's a square root of L on top. So we can write it like this. To me, that's the simplest way to write it. It's 70 times the square root of L over K. QL, I mean, it's going to look at it. It's going to be exactly the same thing. Everything I just said holds. It's just that, okay, the K to 1/2 is now still to the 1/2, but the L is to the negative 1/2, so it winds up in a denominator, right? So, right, it's exactly the same. So it's 70 just times the square root of K over L instead. So now we just plug in those numbers. So don't forget that K is in thousands of dollars. So the number you're actually using here is 250. That would screw you up. So QK of 250 comma 1225 is just 70 times 12, the square root of 1225 over 250. Calculator. That's not exact. I should have put an approximately, but we're just going to say let's just round to the nearest. Well, the nearest what? So the units here, Q is in units of production, whatever that is, whatever this company makes. Gallons of paint, flat screen TVs, who cares? So the rate of change with respect to expenditure of production is 155. So if you spend $1,000, you'll make another 155 flat screen TVs, whatever. Right? So that's the rate of change of production with respect to money spent. Same exact deal with QL. I mean, it's the same math. It's just 70 over, now it's K over L, so it's 250 over 1225 calculator. That rounds to 32. It's just some decimal. And units wise, it's the same deal. That is units produced per labor hours. So if we add one more labor hour, it looks like we will produce 32 more units. Wow, that's a fast worker. All right, so the units there are units of production per labor hour. So I guess this all leads you to believe that maybe this company should be giving its employees more hours and spending less money, because it looks like they're getting a lot more bang for their buck in labor hours. That should kind of make you think of like a max of a function. Are there maxes of functions of two variables? Of course there are. Picture a 3D surface. It's got little peaks and stuff. It's got maxes. So that's kind of the next thing we do is optimization and maximums for things that have more than one variable. And as you may guess, it involves taking a derivative and setting it equal to 0. It's not that much different.